Good morning. Can you hear me? My name is Bernhard Anthony. I work for Plaza & Teurer since 2016, and I'm responsible for the Technology Center of Plaza & Teurer, and it's an honor to me to speak in front of you today. Before I start my presentation, I brought you a picture that I wanted to show or share with you. This is a very important picture, not only for Plaza & Teurer. I think it is also a very important picture for the whole industry. On the picture you can see two men in the front. On the left side it is Franz Plaza. On the right side you can see Josef Teurer, the two founders of Plaza & Teurer. And in the back you can see the very first stamping machine built by Plaza & Teurer. And I think this was not only a milestone for Plaza & Teurer, this was a milestone for the whole industry. The second milestone, of course, was to introduce the assembly line method to the industry. The third milestone is not that far in the past. It was in 2015 when we introduced the first hybrid machine to the market. And now we are in the fourth part of revolution, the digitalization. And not only digitalization, also automatization. And this is what I'm talking about today. How we want to take our part in this revolution. Still, our focus is the track, the permanent way. We still have to deal with this, with the rail, with the sleeper, with the ballast, with the subsoil. This hasn't changed. And this is still our focus, because we believe still that this is the most cost-effective way to make railway running. What has changed, of course, is the superstructure, but also the machinery. And if you think about automatization, you need, of course, a tamping machine and a lot of sensors. For our automatization of the whole tamping process, we are using a laser scanner in the front, also a camera and some line scanners to see the obstacles in the area of the rail. But we also need some intelligence on the machine, because with only the sensors you have nothing. You also need to interpret the data. You have to calculate the actions that the machine has to do with this information. But why are we doing this? We all know we have a lack of operators. It is hard to find young people to go on the machine, especially in night shifts, during the weekend or on holidays. So this is one part why we decided to make our machine smart, to automate the tamping process. Another part is, of course, quality. We want to achieve a better quality during the tamping process, and the infrastructure manager wants to know more about the condition of his track. And we want to avoid mistakes, of course. It can happen, of course. If you are tired in the night, then it could happen that you hit a tie or sleeper, but it should not. Now I show you a small video that will introduce the main points of the automatization to you, how we did this on our machines, and what you can expect from our machines in regards of information. The machine that you can see here is our own machine, owned by Plaza & Teurer, and responsible for that machine is the Technology Center. You can see now the laser scanners in the front, and of course also the video camera to scan the area. And this is the picture that the artificial intelligence produces. So you can see the track, and you can also see the position of the lifting and lining unit, and of course also from the tamping times where they penetrated into the ballast. The operator has the same view, and he has to react on the data processed by the machine, so he has to confirm if the machine has to do the action. As a side note, you can also see that this machine is a fully electric machine. Yeah? So not only the machine is powered by electric, also the tamping units are powered with an electric motor. And this is the result that can be given to the infrastructure manager. So in the end, after the work, you get a full documentation of the whole working process. There you can see the position of the tamping times and also of the lifting and lining unit. And if there are any obstacles in the track, then they are also shown to the operator, and he has to react on that. And what you can hear is nothing, because it's electric driven. But to bring the machine, the lifting and lining unit, and also the tamping banks, yeah, or units into the right position is only one part of the automatization. We know we have worldwide a lot of standards and regulations, and the machine has to be smart enough to deal with that. So this is the second part of the automatization. We have some tamping parameters, like the tamping force, of course. We have the squeezing time that has to be chosen in relation to the ballast condition. We have the numbers of insertion. Yeah. We have some regulations about the tamping depth. And of course, we have some machine parameters as well. And all this has to be taken into account to achieve the best tamping quality. But how do you do that? By research is the answer. Yeah. For that, we equipped the same machine that you have seen in the video with a lot of sensors, yeah, to measure what happens during the tamping process. Therefore, we use some acceleration sensors. We place some strain gauges directly on the tines to measure the forces during the squeezing process, but also during the penetration process. But why did we do that? Because we want to monitor the condition of the ballast in the first step. We want to be able to detect, okay, what level of deterioration the ballast has. Then a side effect is that we can say, okay, when is the perfect timing for ballast cleaning? We can also tell, okay, how is the influence about the different parameters on the compaction quality? And of course, all this help us to find out the best parameter set in regards of the ballast condition and optimize the tamping machine. So in the end, the machine should be able to detect the ballast condition, react on that, and achieve the best tamping quality, and in the end, a long-lasting track geometry. I brought you some examples of our sensors that we used for the research. This will not be necessary for the final product. Therefore, we mounted some strain gauges directly on the tine and compared the measurements of the forces. And with this information, we are able to interpret the ballast condition. Another sensor that is used for our system is an angle decoder. This sensor we are using to monitor the movement of the tine and also of the vibration, and to see how the amplitude behaves during the squeezing process. With this information from these sensors and some additional ones, of course, we took a closer look on the squeezing process. Yeah, you know, the tamping bank is positioned over the sleeper that you are going to tamp. Then the unit is moving down, yeah, to penetrate into the ballast, and then the squeezing process starts. And there are two phases during the squeezing process. First, you have to fill the void underneath the sleeper with enough ballast. If you have done that, then you are able to compact it. And we took a very close look on this whole process. You can see we are generating a lot of data points, over 600,000 data points every squeezing cycle. And this is an example how the data looks. So on the diagram on the left, you can see on the x-axis the time. On the y-axis is the total movement of one tamping time during the squeezing process. So during the closing movement of the tamping times. What you can also see is the cycle. You know, our tamping machines are working with a frequency of 35 Hertz. This means if you have a squeezing time of 1 second, you have 35 times forward and back movement of the time. And additionally, you have the quasi-static movement of the squeezing cylinders. And the whole process that you can see is built in this diagram. So you have the static movement and additionally the vibration from the oscillation. And if we take a closer look on one cycle, here in the red box, we can see with the dotted line, this is when the tamping time is not in contact with the ballast. The blue point is the point where the time gets into contact with the ballast. So it's a contact point between time and ballast. Then they are moving together, ballast and time, as they reach a point where the contact gets lost again. If we take a closer look on the whole cycle, again the dotted line where the time is not in contact with the ballast, the red line is when they have contact. So when they get into contact, of course the forces are increasing until they reach a certain limit. And then also the amplitude reaches a certain limit and the move or the time moves backward. And so the forces are decreasing and then it comes to a point where the contact between ballast and time gets lost again. And then the next cycle starts again and again and again. Here you have it in more detailed. So you can see the maximum forces. You can see the amplitude here on the x-axis. You can see the area that is closed by this butterfly diagram, we call it, is the energy transmitted to the ballast. And all these parameters help us to characterize the condition of the ballast. Because if we know, if we have a squeezing time of 1 second, then we not only get one of these diagrams, we get 35 of them. And if you all take them after each other, then you can do an interpretation of the whole squeezing process. So what you can see on the left side is the waterfall diagram. Again, on the x-axis, the oscillation of the time in millimeters. Here you can see the forces, and this is the number of cycles. And you can see that there is a change, not only in the forces, but also in the energy that was transmitted to the ballast. If you now look on this diagram from the top, you get a heat map. And then you have some additional information of the development of the forces. The darker the color, the higher the forces. What you can see also in this diagram are the points of contact. So when the time gets in contact with the ballast and when it loses the ballast contact again. So you can see in the beginning we have a greater contact as in the end. In this case. When you now compare many data points with each other, many tamping actions, we were able to detect, okay, what is clean ballast, what is fold ballast. We found out that the behavior of the ballast is quite different. On the left, you can see the clean ballast. Why do we have two diagrams? Because it was a two squeezing. So the unit was penetrating 2 times in the ballast and did the squeezing work. And on the right side, we have only one work. What you can see is also that the butterfly diagram looks different. The forces in the full ballast are higher. The energy transmitted to the ballast is also higher. If we then show again the heat maps, it becomes more clear. Yeah? So you have the higher forces here compared to the new ballast. And this information helps us, of course, to categorize the ballast and in the next step to react on this categorization. Because what we see is that not only the behavior of the ballast is different, it is also very important to treat the ballast different. Yeah? This is the step that we are looking right now to find out which parameters are needed to make the perfect treatment in regards of the ballast condition. What we are also doing with the data is to feed our multi-body simulations. I don't know if it is possible to play the video again. With this system model, we have the chance to test a lot of things on the computer without going into the field. And there we can play with parameters, with settings, and see what happens with the ballast, with the compaction. What we also do with this information is to further develop our tamping units, yeah, to make them more robust, and also to fit them to the certain ballast conditions. So in the end, the in situ measurements help us to evaluate, of course, the condition of the ballast in one part, but they also help us for the automatization, because when we know which kind of ballast condition is in the track, then the machine can react on that and achieve the best compaction quality, and therefore also the long-lasting track geometry. Sorry. So in the end, you have seen it on the first video. We have this tamping report with the information from the positioning of the lifting and lining unit. You have also the position of the tines. So the position of the tines is seen in the overview on the top. Here you can see the position of the lifting and lining unit. This is important not only for the infrastructure manager to know, okay, was the switch tamped as it had to be. It is also important for the operator to say, okay, we haven't damaged anything. Yeah. So this is a kind of documentation. But with the system I showed you before, we have also the information of the tamping process. So you can see, was the frequency chosen right? Was the amplitude the one we wanted to have? And did we transfer enough energy to the ballast? What you can see in the energy, this is the diagram here. There is the position on the track, and here is the energy in kilojoule. There are two lines. The black one, I told you, we have a quasi-static movement by the squeezing cylinder. This is the lower line. Yeah, it is about 0.2 kilojoule that we transmit to the ballast by only the static behavior of the squeezing cylinders. From the dynamics through the vibration of our machinery, of our tamping banks, you get the rest of energy that is transmitted to the ballast. This is the blue line. And this is about 2,500 kilojoule. So you can see a lot more energy is transmitted by the vibration shaft than due to the quasi-static movement. What you can also see is this behavior of the energy transmitted to the ballast, and one very important point is this one, because you can see there's a decrease. And the answer is on the next page. You can then take a look, okay, where was it? Where was it in the switch? And you can see there was a double sleeper. So this was the reason why we were not able to get enough energy into the ballast. And at this time, the operator should have squeezed maybe more than one time. Maybe a second time would have been better to get enough ballast underneath the sleeper and then to do the perfect compaction of the ballast. So, automatization is not only to get rid of these operators, no. It is a way to make the work transparent, to support the operators to achieve the best quality in tamping, and of course to make the machine user-friendly, so you maybe find more operators in the future with these kind of smart machines as you do right now. And if you want to know more about the things, the crazy things that we are doing at the Technology Center of Plaza Antora, you could take a look at our homepage. There you will find the area that is called PT Research. There we are publishing a lot of crazy stuff that we are working on, and would be happy if you would find the time to visit the page too. So thank you very much for your interest. Have a nice day. Thanks.